We're now in a position to establish Chebyshev's inequality, which is a tail bound that we stated in data 8 without proof. So the assumption here is you have a random variable that has a distribution, and there's a mean. Use of that triangle to denote where the mean is because the mean is a balance point. That's a common way of denoting where a mean is. What we're going to do is we're going to stand at the mean and look an equal amount on either side. So that gives us two tails. And we're going to try and see how much is in those two tails. Total of two tails. Once again, we can't say exactly what it is. We're going to try and get a bound. So let's try and write down what that event is. That event is that remember the x is a random variable that's on your horizontal axis. And so you're looking at x and you're looking at how far it is from mu x. And what you want is for that distance to be at least c. That's the event that corresponds to that shaded region there. And so what we're looking for is what can we say about that probability. It's the total probability in the two tails. I'm making no assumptions about x being non-negative. What we're going to do to find this is use what we have. We actually don't have properties of the absolute deviation, but we do understand very well the squared deviation. And we note that since the absolute deviation is non-negative and c is non-negative, this event is exactly the same as saying that the squared deviation is at least c squared. And now that squared deviation is a non-negative random variable that we understand. So we are going to use Markov's inequality on that. So Markov's inequality says that this probability is less than the expectation of my random variable, which is the squared deviation, divided by where my tail starts, which on the scale of that random variable is c squared. Do you recognize the numerator? The numerator is by definition the variance of x. And what we have shown is that those two tails together are equal to the probability that the absolute deviation is at least c, and that is bounded above by the variance divided by c squared. And that is Chebyshev's inequality. It looks a little different than what we wrote down in data 8, but we'll see that it's exactly the same. So you have a random variable x. I have no conditions on x other than, of course, there's a mean and a variance. Then if you look at the total probability in the two tails that start at a distance c on either side of the mean, that is at most the variance of x relative to c squared. And again, you get a small upper bound, and if when you are looking at c pretty far out, from the center of the distribution. So this is a tail bound. Markov's inequality is another tail bound, and so is Chebyshev. We're often going to think of the mean as a sort of origin, and then walk in standard deviations on either side. So we have 1 SD. So mu x, and let me call that one standard deviation of x, and then so an equal amount on the other side is another standard deviation of x. Standing at the mean and walking in units of standard deviations on either side is going to become a very common move. And so supposing I go 2 and a bit standard deviations on either side of my mean, and I look at the tails there. Okay, then I can write that event, whose probability I've shaded, as the chance that x minus mu x, that is the distance between x and the expectation, is at least as large as some constant z times the standard deviation. And Chebyshev's inequality tells me that this is then less than the variance relative to the square of my constant, and that is 1 over z squared. And that is the form in which you had seen Chebyshev's inequality in data 8. It tells you that no matter what the shape of the distribution, the chance that your random variable is at least as large as, how about 5 standard deviations? That is at most 1 in 25. The chance that it's that distance is at least 3 standard deviations is at most 1 in 9, and so on. And so what this way of looking at Chebyshev's inequality is telling you is that a random variable is typically going to be within a few SDs of the mean. Mean plus or minus 5 SDs picks up, 96% of the data, right? 96% of the probability is in the range mean, at least 96% of the probability is in the range mean plus or minus 5 standard deviations. So your distribution, no matter what its shape, is going to put the vast bulk of its mass on the interval mean plus or minus a few SDs. And that's one reason the SD is a useful measure of spread. Any result that starts with no matter what the shape of the distribution, that's a powerful result. Now there's one thing to note here. This is a bound on 2 tails. What if I wanted a bound on just 1 tail? What if I wanted to know only what the right-hand tail is? It's tempting to divide by 2, but you can't divide by 2. Look at that picture. Those 2 tails aren't equal. So remember that this is a bound. It's not an exact value, it's not an approximation. The bound on 1 tail is less than or equal to, and I'll write informally here, is less than or equal to the sum of 2 tails, which is Chebyshev's bound, 1 in 25. So the upper bound on the total of two tails is also an upper bound on a single tail. You cannot divide by 2 because there's no assumption of symmetry of the distribution. If the distribution were symmetric, you could divide by 2, but in general, you cannot. So be careful. Just remember that this is a bound.